Voltage divided bias with emitter bias configuration. Today's class will discuss how to do DC analysis of voltage divider bias with emitter bias configuration. Let's draw the circuit diagram, DC equivalent circuit diagram for voltage divider bias configuration. Okay, can you see that last class we already said about voltage divider bias with emitter bias configuration. From the last class, the circuit whatever we written for this voltage divider, we written the DC equivalent circuit eliminating the AC sources and as well as capacitors. Resulting circuit is going to be this. In the previous circuit amplifier circuits, you have not shown currents, but here you have to show currents and voltages. You can say I1 is the current going through RB1 resistor and I2 is the current going through RB2 resistor. In this branch, whatever the current going, which we labeled as I2, and of course the current going through emitter resistor, which we labeled as I emitter current, and current going in the collector branch, which we labeled as IC. Voltage between the base and emitter, which is VBE. Voltage between collector and emitter, which is DC, collector and emitter voltage. Last class, we said that the circuit can be analyzed using the, if you want to perform DC analysis, there are two techniques are there, two methods are there. One is accurate method, other one is approximate method. So today's class will work out both things. Accurate method. Accurate method of DC analysis. Accurate method makes use of a theorem called as Thevenin's theorem. Thevenin's theorem is a very popular theorem in network analysis, electrical network analysis. We will convert this circuit into the Thevenin's equivalent circuit, so that this input section of this input section in the sense which contains supply voltage RB1, RB2. This particular section I am going to use Thevenin's theorem to simplify this input section. Okay. Whereas the output section will be retained as it is. Okay. We will not make any changes to the output section. Output section which contains RC, this transistor, and as well as RB. This section will not change since input sections will modify as per the Thevenin's theorem. So we can write the Thevenin's input section. We can write it here. You can see that how I am going to modify. You can see that we have a voltage source followed with the resistance here, RB1, RB2, whatever we have seen in the previous circuit. That can be modified in this fashion. You can see that. So let us call this as supply voltage is VCC with plus and minus. This is RB1, RB2, this is RE. And rest of the circuit we not write it. Because anyway this section we are not going to modify, right? Left section as it is. Any changes I did from this circuit to this circuit? I don't think so. I have not done any change, few changes. You understand this circuit? How I got this circuit? Only this portion. Just reverse power supply, that's all. Okay. So that it means a separated power supply, that's all. You see that you want to look at the separate version. You see that one VCC may come here, another VCC which is here, right? And even the ground also, of course, you can see there is a ground here, the common ground. Okay. Only thing is in this circuit, I have not written this portion complete, that's all. Right? This VCC added here. Okay. Plus to the base of transistor, you can see. Plus to the RB1, you can see that is connected as this. You understand this? Any changes? No changes from here. Right? Okay. I will retain this original circuit as it is. Okay, now we can apply Thevenin's theorem. I will write the Thevenin's equivalent of this input section. As we said already, input section consists of VCC, RB1, RB2. For this, to make this simplification, we apply the Thevenin's theorem. Any question from here to here? Translation? Have you understood this? How we got this circuit? Let us give name for this input section of this is a figure which represents input section of voltage divider bias. Voltage divider bias configuration of circuit. So in this second figure, what you are observing is we just showed the input section in detail. That's all. Okay, so that the next stage we can apply Thevenin's theorem. So now let us show the Thevenin's equivalent circuit. I am going to modify this input section by using the Thevenin's theorem, which I am going to write it here. We have a power supply, which we will label it now VTH. Subscript TH stands for Thevenin, and V stands for its voltage. So this can be labeled, this can be referred as Thevenin's voltage. Okay, we will explain this what is Thevenin's voltage. How to obtain this Thevenin's voltage from this circuit diagram. We will explain it later. For the time being, you can take down this circuit. This is Thevenin's voltage. In series with this, you will have a resistance, which we will call as Thevenin's resistance. I will show you the procedure how to calculate Thevenin's resistance and Thevenin's voltage having circuit on this side. Okay, so that's going to be, and we will write rest of the circuit as it is. We will have a ground here, and of course we will have a transistor. Anyway, the output section we are not going to change it. output section will have the emitter resistor which is RE, and the rest of the section circuit will be as is. This is going to be Thevenin's equivalent of the input section of Thevenin's equivalent of the input section of voltage divided by current. So just you represented your circuit diagram with an input section, replace it with Thevenin's equivalent circuit. We will write here what this R Thevenin represents. R Thevenin is Thevenin's equivalent resistance. Thevenin's equivalent resistance. Similarly, Thevenin represents Thevenin's equivalent voltage. Okay. How will you understand now how you obtain this? So far, what you have done from the voltage divider bias configuration, we return the DC equivalent by eliminating the capacitors and AC signal sources. So to analyze this under DC conditions, we are using two methods. One of them is accurate method. Accurate method makes use of Thevenin's theorem. Okay, we will see that how to apply Thevenin's theorem to this DC equivalent. First step, what we have done is we just return the alternating version of the input section. You can see here. Okay. The input section comprises these elements. Okay. This corresponds to input section. The input section, okay, can be replaced by Thevenin's voltage source and Thevenin's resistance by applying Thevenin's theorem. Here we are not going to explain the basics of Thevenin's theorem or the statement of Thevenin's theorem. Any complex network like this, which contains multiple resistances, multiple voltage sources, can be replaced with Thevenin's voltage and Thevenin's resistance. Suppose you might have a circuit with hundreds of resistors like this, or hundreds of loops like this. Is it possible to simplify all loops by applying KVL and KCL? Think about it. Suppose if I have 10 loops, I will result in 10 equations. Right? Okay. One loop will result in one equation. If I have 10 loops, definitely I will result in 10 equations. Solving 10 equations in mathematics, you know the complexity. It's very difficult. So for that, the best theorem is going to be Thevenin's theorem. What Thevenin's theorem will do is let the number of loops, any number of loops, it may be circuit, but all number of loops will get simplified to only voltage source and resistance. Understand? Any complicated circuit can be simplified to just one voltage source and one resistance which is in series with the voltage source. So it is very simple to apply using Thevenin's theorem. That's what we did here. So our circuit contains two resistances, and of course if you want to apply the two KVLs, you want to apply for this. For that complexity to simplify the complexity in voltage divided bias, we identified the input section. For this we applied Thevenin's theorem, and we came to know that you want to estimate from this Thevenin's theorem the values like P Thevenin and as well as R Thevenin. Now the question is, how do you estimate the R Thevenin having this circuit? So the simple technique is, when you want to estimate R Thevenin, the value here from this circuit, what you must do is, if you have any DC voltage sources, short circuit it and find out the effective resistance looking from this side. That becomes the value of R Thevenin. You understand this? How to calculate R Thevenin? If you have any voltage sources in this input section, just replace with short circuit. So you have voltage source here. You virtually do it, need not do it physically by short circuiting it. Okay. Assume that this voltage source does not exist when you want to calculate RT. Now looking at this side, what is the equivalent resistance of the of this particular input section? With these two are parallel. Okay, that becomes your RT. So RThevenin is nothing but it is a RP1 parallel with RP2. That's the expression for RThevenin. So write it here. The RThevenin is nothing but RP1 parallel with RP2. Or else you can write this one as the product of RP1, RP2 divided by RP1 plus RP2. This is the value of RThevenin. Understand the procedure? How to calculate RThevenin? RThevenin can be determined from the circuit by short circuiting the voltage sources, DC voltage sources. We have DC voltage source here, you just short circuit it. You must short circuit DC voltage sources. Apart from this, what you must do it after short circuiting? Find the equivalent resistance of the circuit. Find equivalent resistance that becomes equal to RThevenin. You understand the procedure to calculate RThevenin? Okay. When you are calculating Thevenin's resistance, there should not be any voltage sources. Okay. DC voltage source. Anyway, we have applied this for the DC equivalent circuit. This of course does not have any AC sources. Okay. Even though when you want to apply the Thevenin's estimate the Thevenin's resistance in the loop, whatever you are considering to apply to Thevenin's theorem, in that loop there should not be any voltage sources. That's what the first one. Short circuit, this stands for short circuit DC voltage sources. Later on, what you do after short circuiting? Find out the resistance of the circuit. Okay, from which you are finding from the input section especially here. That gives me the value as this. Okay, so that's going to be the Thevenin's resistance. How do you find out Thevenin's voltage source? V Thevenin. So V Thevenin is nothing but looking at this side, what is the effective voltage across this RV2? That's what will be your V Thevenin. Understand this? Looking from this side, okay, now you should have voltage source. You should not make voltage source 0 when you want to calculate the Thevenin's voltage. Only at the time of calculation of R Thevenin, voltage sources should be made 0. But while calculating V Thevenin, voltage sources must be there. So now looking at this side, what is the voltage, effective voltage across the RB2? That gives you your V Thevenin. Anybody can get the value of V Thevenin? Voltage across RB2. Anyone? Bit difficult, right? I want VTH, which is nothing but voltage looking at this side. I am asking simply what is the voltage across RB2? We have supply voltage here. You have to apply voltage division rule there. So V Thevenin is nothing but VCC times RB2 divided by RB1 plus RB2. This is a simple way to calculate this. When you want to calculate voltage across this, just take the supply voltage, multiply with resistance across which you are calculating the voltage is RB2 divided by sum of these resistances. Okay. Do you understand how to calculate V Thevenin? Okay. Now you see that this very big circuit was simplified to this particular circuit. Okay. Now my original circuit I will try to modify it. Okay, so whatever you are seeing circuit now, I will replace it with this. Now having this circuit we can apply now, we can simplify it, right? Because the complete circuit now, RB1, RB2 which was inside this now, is in terms of RThevenin, right? You can see RThevenin which contains RB1, RB2. Okay, and even VThevenin also contains VCC. So now this circuit can be simplified. You can apply KVL to the input section, and then you can obtain the operating point values IC equivalent as well as VC. Right? That's what you want to obtain from the DC equivalent circuit or DC analysis. Okay, straight away applying this KVL or KCL to this is very difficult. It will result into different equations. Simplest way is going to be converting the DC equivalent circuit to the Thevenin's. This is called Thevenin's network. Thevenin's network, and for this you can apply KVL to the base emitter section, which will get the expression for IB, and from that you can find out the expression for IC. You can apply KVL for the collector emitter section, which will get the value of VC, right? Then you can follow it. Okay. Now let me take a modified version of this complete circuit of Thevenin's equivalent. I think this circuit is no more needed because we already translated to the VThevenin. Now rewrite the Thevenin's network, complete Thevenin's network. Thevenin's equivalent circuit of voltage divider bias. Okay. What I have done here is, in this case I have not written the complete circuit, here I have written complete circuit. Right here, our Thevenin, which is RB1, RB2 divided by RB1 plus RB2. Okay. Similarly, VThevenin is equal to VCC times RB2 divided by RB1 plus RB2. Okay. Now we have rest of the circuits. Any questions here on these things?
Sir, in that circuit you have two separate sources. VT has and
Yeah, this sources, this is VThevenin, okay, which incorporates VCC.
But
Input section.
yes, but won't it be VT across RC also?
Correct, you are correct, but here this is for color output section. Because this inside this there is a VCC which is embedded in the one value solution. Okay, now we can find out the operating point by applying KVL to the input section and find out the operating point. Apply KVL. This is our input section. Okay, whatever current flowing here, which we will call as IB, current which is flowing here, call as IE, current flowing in the collector, call as IC. This is our base emitter. Base emitter section. Now let us apply Kirchhoff voltage law to base emitter section. you get. Start applying VThevenin. I'm starting from here. You can start from the ground. If I go in this way, okay, minus VThevenin plus IV times RThevenin plus estimated drop across Thevenin's resistance. We have a drop across base and emitter plus VBE plus I times R plus I times RE, which is equal to 0. Any questions in this KVL equation? This is again, as usual, we obtained equation what we obtained in the emitter bias, right? Substitution here is IE. You know that what is the IE expression? You already derived 1 plus beta times. I will substitute that here. Substitute IB as IE as 1 plus beta times IB in the above equation. What will be the resulting equation? Minus V Thevenin plus IB times R Thevenin plus VBE base emitter voltage plus instead of IB we have 1 plus beta times IB times RE, which is equal to 0. Take out IB as common factor as we did for emitter bias. We have an IB here. The rest of it can transfer to the right hand side. IB to take a common factor, we have left out with R Thevenin. From this we have left out with 1 plus beta times RE, which is equal to V Thevenin minus VBE. We transfer these two things to the right hand side. I just want an expression for IB. The base current IB, which is equal to, you send this to denominator. So V Thevenin minus VBE divided by R Thevenin plus 1 plus beta times R. This is the expression for this. Once we know the expression for base current, it is easy for us to calculate quiescent electric current expression. So we know that IC electric current, which is equal to beta times IB, which is equal to beta, you can keep it as a gain factor outside. Numerator will be V Thevenin minus VBE divided by R Thevenin plus 1 plus beta times R. This is the expression for you can make it here. This is also equivalent to IC quiescent. Again, we can approximate this as we did in the previous two bias circuits. VB is very small compared to the Thevenin's voltage. You can look at here the expression for Thevenin, which is VCC, which is a large quantity, multiplied with this resistance, this becomes again larger, right? Compared with these two things. Okay. So that V Thevenin is larger. So V Thevenin is larger compared to the base emitter voltage. So this can be neglected. Since VB is very small, this quantity is going to be very small, that can be negative. The resulting equation for IC, which is equal to ICQ, which will be in the numerator we are of course with Thevenin voltage, but in the denominator we have R Thevenin plus 1 plus beta times. This is the final and simplified equation for beta is the most. Fine. Any questions? I'll try to apply KVL to the other telemetry section and find out the expression for VC. It's almost same as chemical bias. Go ahead. Apply KVL to the collector emitter section. Find out the expression for VCQ. So I want to apply Kirchhoff voltage for collector emitter section. This particular section. Okay. See, this is minus VCC plus IC times RC plus VCE plus IE times RE, which is equal to 0. It's the same as one which we have studied the emitter bias circuit, right? VCE. Have I'm not expert how to simplify this. Substitute IE, since IE is approximately equal to IC. In place of IE, you can substitute as IC. And you simplify this, take out IC as a common factor, and simplify this, you result in equation VCE is equal to VCQ, which is VCC minus IC times RC plus R. This is the expression what you get it after the simplification. Okay. Here I present collector current and present collector voltage expressions. You must remember these expressions, otherwise it will be difficult for you to solve problems on voltage and RC. Okay, so try to relate the expression for VCQ, which we already written here, and ICQ, rewrite beta times V Thevenin minus VBE divided by R Thevenin plus 1 plus beta times R. These are the 2 points which we estimated. These 2 are called as Q points of voltage divided by C. Okay. Fine. We go to next method, which is approximate method. How to obtain the operating points, same operating points what we are seeing here, through the approximate method. We will go through that. Any questions here? Approximate method will not make use of this theorem or Thevenin's theorem. It is based on certain conditions. What are those conditions which illustrate in the approximation? Is there any questions here so far? Okay. Fine. So we will go through the next procedure of DC analysis. Approximate. DC analysis. Using approximate method. Here you need to satisfy certain conditions. Alright, just an again in this approximate method also, we will not do any changes for the output section. But only thing is we modified obtain this modified circuit of the input section. Look at this how we modify the input section. I am writing the input section in this way in approximate method. Write the DC voltage source, which we indicate with plus VCC. And we have as usual the resistance which is RB1 and the resistance which is RB2 with grounded other end. And here we have equivalent resistance which I will write it as RA. And we will write this particular resistance in the dotted structure manner where RA is approximately equal to 1 plus beta times RB. And whatever current flowing in the RB1, which we will label it as I1, current flowing in RB2, which we label it as I2. So for this, we can give a title as figure title as caption as approximate method analysis. Approximate method of analysis of voltage divider bias. Okay, look at the approximate conditions here which you need to satisfy. Any questions here while drawing this circuit? This is not a complete circuit, and look at this what you have done here. This VCC is retained as it is, no changes, and RB1, RB2 as usual you can see there. Currents also written the same currents whatever is flowing. But rest of the circuit, whatever the resistance offered by this and the input section that we indicate as R. The input resistance offered, you see here somewhere we have a transistor here. Okay. This transistor at this particular point, when you look at this particular point and the input side, what is the resistance offered by the circuit? Normally you know for the current flow, whether it's medium resistance or large resistance, it depends upon the circuit. But here what I am trying to do is the input section, okay, whatever you are seeing from this side, what resistance offered by this, replaces with this resistance. And this resistance RA is nothing but its expression is given as 1 plus beta times R. If you look at the expression of affiliate method, look at the denominator of IV expression. There you will see that R Thevenin plus 1 plus beta times RE. In numerator you can see there is a supply voltage there, so we write the expression into 1. So the expression for IV is nothing but V Thevenin minus VBE divided by R Thevenin plus 1 plus beta times R. Right? The same expression. Right? Look at this expression now. This is the input current and this must be the input voltage, effective input voltage, numerator whatever you see here. And look at this, what must be this then? Okay. This is input current and this is the input effective input voltage. What must be this then? It must be input resistance. According to the Ohm's law, I is equal to V by R plus R. So this is the input current and this is the input voltage, effective input voltage I am saying, because you are going to subtract whatever the voltage, because here the two resistors are there. You get here the V Thevenin minus VTE. You must negate the drop across the base emitter and this is the source voltage which contains it. This will be the effective voltage across your input section. Okay. And this is the input current, obviously this must be the input resistance. And if you look at this terms present in denominator, this R Thevenin term is there and 1 plus beta times R E term is there. And again, if you compare these two terms here, obviously the R Thevenin term is changing important. If you look at RB1 and RB2, say assume that there is a 4 kilo ohm resistance RB1 and RB2. So, what's the parallel combination of those things? Very small. Compared with this 1 plus beta times RE, when you compare this, obviously this becomes a small quantity. The effective overall large resistance is present in this circuit. So, due to that, I can ignore this. Okay. Now, if this is the input current and if this is the input voltage, obviously my input resistance will be this. So now I can replace this with virtual resistance. That's why I written in the dotted line. It's virtual resistance here. the resistance of this the remaining the rest of the circuit is given by Ra, whose mathematical expression is Ra is approximately I'm saying here, I'm not saying exactly. Approximate is because I am ignoring the term here R thevenin. So that's why Ra is approximately equal to 1 plus beta times the Ra. Okay. So now we'll see that we'll assume some conditions here to derive the quiescent electric current as well as quiescent electric voltage. That's what our intent, okay. In the DC analysis, we must estimate the quiescent electric current, quiescent electric voltage. Previously, we estimated that using Thevenin's theorem, but here we are not making use of Thevenin's theorem. But what we have done is input section, written the input section part of the circuit as it is, but rest of the circuit resistance we replace with the Ra. This resistance is called the virtual resistance, and the expression is given like this. And look at here, I am assuming that here, suppose if Ra is going to be very much larger than this value, what will happen? Okay. Suppose here current whatever is flowing, let me indicate as IB. There are three currents are here. One current which is coming here, other current which is going to the ground, and another current IB base current which is going to the transistor input. And this current will experience this amount of resistance. Okay, look at now here. My condition here is, as we said already, approximate method depends on certain conditions. The condition here is, if R is going to be very much larger than the RB2, what is going to happen to this current? Current will be less. If I assume very much larger, say this RB, this Ri is going to be very much larger than the RB2. If that is the case, maybe 10 times, 100 times larger. If that is the case, what will be the current flowing through this IB current? Very small. If this current becomes small here, if it is negligible, then definitely I1 current flowing here will be exactly equal to 8. So this current becomes neglected because this value is going to be very, very large. If that is the case. So these are the assumptions what we are going to make it right now. So according to that, we write and here whatever the voltage here at this particular point, let me write it here as voltage as VB, and condition here is I will rewrite again this circuit. It's a condition. I will show here in this circuit. This is the virtual resistance which we indicate with dotted lines, and this resistance is going to be Ra. Okay. This is plus power supply VCC. This is RB1. This is RB2. And if I assume that this Ra is going to be much more larger than the RB2, if that is the case, what will happen to this current? Already we assumed it current flowing here is I1, and current flowing here is now it will become I2 will be exactly becomes equal to I1 approximately, because we also we are assuming that Ra is far greater than RB2. Okay. So this current whatever it is flowing here, IB, that will become 0 if this quantity is very large. So this is the again we can give title same as this. This is figure is approximate analysis. Now, what is the voltage at this particular point? If I label this point as a VB, what is VB? Voltage across RB. That means I am ignoring this portion, that's all, because current becomes less. I am ignoring this particular point because whatever current here is becomes 0, and this point is going to be very large compared to this point. Okay. Then what is the voltage at this particular point? VB is equal to, again voltage division rule, VCC times RB2 divided by RB1 plus RB2. You understand how we obtain VB? In other way, I can say that VB is nothing but voltage across RB2 or voltage across this resistance. When this becomes zero, maximum drop occurs across this way or this, because the parallel voltage remains same. Okay, even the voltage drop across this will be same as voltage drop across this. So how do you estimate VB now? VB is nothing but this particular voltage across this voltage. Is nothing but the supply voltage times the resistance divided by sum of these resistances. Okay. That's going to be the VB. Already you know that from the basic of transistor, VB is equal to VB minus V. From this we can estimate what is V. So V can be estimated as, if you want to simplify this as V, it becomes VB minus VB. These equations you must remember, because in the examination when they ask you to solve the problem using the approximate method, these equations are required for you. Without which you want to derive it in exam, it becomes difficult. And having this V, can we estimate RE? So that can be done using what is the expression for V? Drop across this resistance. But this is another end is grounded here. V minus 0 divided by V is equal to definitely IE times RE. I just want to calculate RE from this, or IE from this. Expression for emitter current is given by VE divided by RE. This is the expression for the emitter current. If you know emitter current, do you think calculation of collector current is difficult? You got my point? If you know the emitter current, calculation of collector current is very easy, because this current is approximately equal to collector current. So I can write this IC is approximately equal to V divided by R. And of course, for this circuit, even though if you apply KVL for collector limit loop, you will result in same VC. So VC, this is actually the way you want to find the collector current, and the VCE is given by VCC minus IC times RC plus R. This is the expression for VC. So go through this, all these equations if you have any questions. Any questions here? This is approximate method. But here conditions, do you know what you mentioned here? The condition here is this RA must be much more larger than the RB. Typically, if you take up here, the condition required is RA is nothing but expression available here. 1 plus beta times RE, that must be larger than 10 times R2. If any circuit, if this particular circuit, if it satisfies this condition, then definitely all these equations are valid. Otherwise, if any circuit, especially this circuit approximate method what we did here, if these formulas wants to sustain, then this condition has to be satisfied. If this condition is not satisfied, whatever derived so far will not be valid. Okay? Understand this? This is the approximate. So typically, 1 plus beta times RE, what is this? This is RI. This must be 10 times larger than R2 for these equations to be valid. Otherwise, this equation. That's a DC analysis of voltage dividers. It's one of the most powerful biasing circuit among the various biasing circuits so far what we discussed. So this circuit offers improved stability compared with fixed bias circuit and emitter bias circuit. That's why this kind of circuit is used in common emitter amplifier. This is what you are going to do in laboratory also. Okay, common emitter amplifier. There you see that developing common emitter amplifier is very easy. That's all. Whatever you are seeing this for the circuit, you want to apply capacitors and AC signals. This will act like amplifier. Okay, if I ask you to create common emitter amplifier for laboratory purpose, what you can do is direct same circuit, add 2 capacitors, one on input side, other one on output side, along with AC sources. Even lots of people has done modification to this flow because total circuit has not been changed. Only small modifications have been done for this. Especially they have started including the capacitor here. called as a bypass capacitor. CB we will see. Adding capacitor there, look at DC analysis will change if I add a capacitor there. You got my question now? What I am trying to say? If I add a capacitor there, anyway for DC analysis we will not use capacitors. This capacitor will be open circuit. But look at for AC how this behaves.